Hello everybody, welcome to a new episode of Inequality. Today we look at an interesting inequality as the following. The factorial m factorial is bounded by m over e power of m and m plus 1 over e power of m plus 1 and times e. And we recorded definition of E is the limit as m goes to infinity of 1 plus m power of m. And in order to show the inequality today, we have to show it in 3 steps. Step 1 is I consider as problem 1 is we're going to show xn is equal to 1 plus 1 over m power of m, and Zm is equal to 1 minus 1 over m power of m as increasing sequence. Missing an s here. In secondary, we're going to show ym is equal to 1 plus 1 over m power of m plus 1 is a decreasing sequence. If you notice that xn here is actually the limit of xn is actually equal to e. And we also look at yn here is the limit of yn is equal to the limit of m goes to infinity equal to 1 plus 1 over m power of m plus 1 is equal to m goes to infinity is 1 plus m power of m times the limit of m goes to infinity 1 plus over m. And we know that the first bit is converged into e, and the second bit just goes to 1. So the limit of yn and xn is both goes to e, so we can, and x is increasing sequence, yn is decreasing sequence. We can see that e is bounded by yn is less than xn, in particular is less than x1 and less than y1. Okay, so let's begin with our first step. xn and zn are both increasing sequence, so that is xn is less than xn plus 1, and that is 1 plus m over power of m is less than 1 plus m plus 1 over m plus 1. So in here, if we y that y m plus 1 loop of xn is equal to m plus 1 loop 1 times 1 plus xn, which is 1 plus 1 over m power of m. And in here we have m plus 1 number of element, so that is actually the geometric mean. If we notice that actually geometric mean of that is geometric mean of m plus 1 terms with x1 is equal to 1 and x2 is equal to x m plus 1 equal to 1 plus n. Therefore, by the inequality we're showing last time, that geometric mean is always less than arithmetic mean, which is 1 plus. Okay, let's do it in this way. So that is actually power of m times x1 to all the way m plus 1 is less than equal than x1 plus x2 plus xm plus 1 over m plus 1, and that is the arithmetic mean. And that is equal to 1 plus 1 over m plus all the way to 1 plus 1 over m divided by m plus 1 and that is equal to 1 plus m times 1 plus 1 over m divided by m plus 1, and that gives m plus 1 over m plus 1. That gives us 1 plus 1 over m plus 1. Now if we okay, so if we multiply m plus 1 power to both sides, we get xm, and by the way that is equal to xm plus 1 power of m plus 1 is less equal than, so we got that xm is equal to 1 plus 1 over m power of m less or equal than 1 plus m plus 1 power of m plus 1, that is x m plus 1. So now we look at set n. We also want to see set n equal to 1 minus 1 over m power of m is also increasing sequence. That is means we also want to show that it's less than 1 plus m plus 1 power of m plus 1 is equal to set of m plus 1. And by similar argument, if we see that square root of m plus 1 set n is equal to m plus 1 root of 1 times 1 minus 1 over m power of n, and that is also the geometric mean, so it must be less than arithmetical mean 1 plus m times 1 minus m over m plus 1, and that gives us m plus 1 minus 1 over n plus 1. And that is equal to 1 minus 1 over n plus 1. Why? If we notice that, so we also taking the power of plus 1 to both sides. That gives us Zn is equal to 1 minus 1 over n power of m is less equal than 1 minus n plus 1, 1 over n plus 1 power of n plus 1. That is equal to Zn plus 1. Now we look at the second problem. Yn is equal to 1 plus 1 over n power of n plus 1 is a decreasing sequence. To do so, some of you might notice we need to use problem 1, so let's begin. Oops. What we want to show is that Yn is greater than Yn plus 1, and that is 1 plus 1 over n power of n plus 1 greater than 1 plus n plus 1 power of n plus 2. So we write that Yn is equal to 1 plus 1 over n power of n plus 1 that is equal to n plus 1 over n power of n plus 1, and that is equal to 1 over n plus 1 power of n plus 1. And notice that this bit is just equal to Zn plus 1 actually is equal to Zn plus 1 as we shown in here. So that is equal to 1 over Zn plus 1. And since Zn is increasing sequence, so it's less than Zn plus 1. Therefore 1 over Zn, and that is also greater than 0, is greater than 1 over Zn plus 1. That is equal to Yn, and that is equal to Yn minus 1. Therefore, we have shown that Yn is decreasing sequence. And also, if we going back to what we have, is we can see that Yn and Xn, they are both approaching to the limit E, and Xn is increasing and Yn is decreasing. So if we draw in a picture, probably would be something like that. That is E, and that would probably be the sequence of Xn is not continuous, but I'm just drawing it for a picture. So yn is decreasing, they're both getting more and more close to e. And it's probably worth to compute that x1 is equal to 1 plus 1 over 1 power of 1. That is equal to 2. And ym is equal to 1 plus 1 over 1 power of 2, and that is 4. So we know that e is bounded between 2 and 4, but if we compute that, in particular, if we compute that y5, so in particular x1 is less than xn is less than e, and less than yn is less than. If we compute y5, that would be, actually gives us 2.9859A4, and that is less than 3. So we have a nice bound of e is between 2 and 3. So now let's go to our final goal of today, which is the inequality. So nice theorem that m factorial is bounded by m over e power of m and e times m plus 1 over e over m plus 1. So we and we consider this part is the first part of inequality, and the second part, and that is the second part of inequality. So we're doing them one by one. So proof. We're showing it by induction. Actually, we're doing proof by induction. So for base case, when m equal to 1, we got 1 over e power of 1. And that is clearly less than 1, which is equal to 1 factorial. So we have the base case. And by induction, we assume that k over e power of k is less than k factorial for some k greater than 0. And what we want to show is k plus 1 over e power of k plus 1 less than k plus 1 factorial. And k plus 1 over e power of k plus 1, we can write that as k plus 1 over e power of k times k plus 1 over e, and that is equal to e power of k. We want k power of k at the top, so we need to divide it by k power of k, and we keep in k plus 1 power of k and times the remaining, and that gives us k over e power of k dot e k plus 1, and k plus 1 over k is equal to 1 plus 1 over k power of k. And notice that 1 plus k over k is xk, so it's a increasing sequence, so that must be less than k over e power of k times k plus 1 over e times e. And e cancel out, so we got that. And also notice that e over k over e power of e, that is less than k factorial by assumption. Times k plus 1 is equal to k plus 1 factorial. So we have proven the first bit of inequality, m over e power of m less than m factorial. Now we want to show the second bit. Now the second bit, for the case 2, we want to show m factorial is less than e times m plus 1 over e power of m plus 1. And similarly, we use induction, so for base case, m equal to 1, we got e times 2 over e power of 2, and that gives us 4 over e, and we have shown that e is between 2 and 3, so that is clearly greater than 1, which is equal to 1 factorial. So base case tick. And now by assumption, we assume that k factorial is less than e times k plus 1 over e power of k plus 1 for some k greater than 0. And we want to show, I personally found it really useful to remind us what we want to show. K plus 1 factorial less than e power of k plus 2 over e power of k plus 2. And e times k plus 2 over e power of k plus 2 is equal then e times k plus 1 over e power of k plus 1 times k plus 2 over e, because we want to divide that in terms of this form, similar to this form above, so that gives us e power of k plus 1 over e plus 1 over e power of k plus 1. Times k plus 2 over e. And also since k plus 1 over e plus 1 over e is greater than k plus 1 over e, then we have that is greater than e power of k plus 1 over e gives k plus 1 times k plus 2 over e. And by induction, we know this bit e times k plus 1 over e power of k plus 1 is actually greater than k factorial times k plus 2 over e. And also, since k plus 2 over e is less than k plus, and also since k plus 2 over k plus 1 is less than e, therefore we got that k plus 2 over e is less than k plus 2. Therefore, the whole thing is greater than k factorial times k plus 1. That is equal to k plus 1 factorial. So we combine step 1 and step 2. We have shown that m factorial is indeed bounded by e power of m plus 1 over e, and m over e power of m. Okay, that's all I got for today, and thank you for listening. See you in the next episode.